All right, this one is actually tying back with your circular motion chapter. Now, in this chapter for gravitational field, you will learn something called satellite orbits. All right. Now, if you have any bodies that orbit a planet, that object or body is a satellite of that planet. You have man-made satellites and you also have natural satellites. For example, the moon is a natural satellite of Earth and Earth is a natural satellite of the sun. Okay. Now let's just consider the case where you have a man-made satellite that's traveling in circular orbit around the Earth. Okay, circular orbit. So this one is your Earth, this one is a satellite. It moves in circular orbit like this, right? Now, since this satellite is moving in a circle, from the previous chapter, you already learned that for something to move in a circle, you must have centripetal force in order for your object to move in a circle in the first place. And centripetal force needs to be provided by some other existing force. For the case of the satellite, your centripetal force actually came from your gravitational force. Because your satellite has small mass m, your Earth has big mass m, you will have gravitational force being exerted on the satellite by the Earth. This gravitational force is actually your centripetal force. It's providing you your centripetal force. So I can say that Fg is equals to Fc. And from here, you can actually use to find some other variables. For example, you can actually use it to find your linear speed v. If you know Fg is Fc, gmm over r squared is mv squared over r, you simplify it, you're going to get v is equals to square root gm over r. Okay. If you want to use it to find some other property, let's just say angular velocity, you can too. You can just say that since Fg is Fc, Fg is gmm over r squared, Fc is mr omega squared. You simplify it, you're going to get omega is equals to square root gm over r cubed. Okay, so this one is tying back to what you learned in circular motion. Here you're saying that gravitational force is your centripetal force. Okay, so that part is okay, right? Then there's another part called Kepler's third law. All right. Okay, guys, can you just excuse me for a minute? I need to get something to drink. My throat is hurting. So just give me 1 minute. Let me just get a cup of water. All right. So, okay, right. Sorry for the interruption. Okay, right. So there's the other part here, which is talking about satellite orbit again, but this one relates to something called Kepler's third law. All right. Now, you don't really need to know what's the definition of Kepler's third law. You really just need to know that Kepler's third law relates to this equation, where we tell you t squared to r cubed is equals to 4 pi squared over gm. All right. Now, Kepler's third law applies to any object. It could be a planet, a moon, or satellite that is in orbit around another planet. Let's just say that the objects that are orbiting right now has mass small m, and the object they're orbiting has a mass big M. We know that the centripetal force is provided by the gravitational force. Eventually, if you make use of this relation, you will come to this equation. The derivation is at the bottom here. The derivation is something that you need to know, okay? The derivation in these colored boxes here are required in your syllabus. You need to know how to derive them, okay? That's the only requirement from the syllabus. You need to know how to derive it, okay? That equation that results is known as Kepler's third law. Now, specifically, Kepler's third law tells you this. The square of your orbital period will always be directly proportional to the cube of your orbital radius, okay? So how to come to this conclusion is through this. If you look at this equation for Kepler's third law, t squared over r cubed is 4 pi squared over gm. If I tell you 4 pi squared over gm is constant, t squared is proportional to r cubed, right? Because I can rearrange this as this, right? Sorry, I can rearrange this as t squared equals to 4 pi squared over gm r cubed, right? So if 4 pi squared over gm is constant, t squared is proportional to r cubed. All right. So it's from here that you get this statement, right? The square of the orbital period is directly proportional to the cube of your orbital radius. That's what Kepler's third law is trying to tell you. Now, specifically, one of the things about Kepler's third law is also this. If you rearrange the equation there from here to this one, you will see that this equation can actually be approximated to a straight line equation, where we tell you the y-axis is t squared, the x-axis is r cubed, and then the gradient is actually going to be 4 pi squared over gm. All right. Now, if you were to plot a graph of, say, t squared versus r cubed, like the ones that is being shown right over here, what you're supposed to get is a straight line that passes through the origin. Okay. So this one, you get a straight line that passes through the origin. Okay, so that equation not only tells you that t squared is proportional to r cubed, it also tells you that you can plot a straight line through the origin, provided you plot t squared against r cubed. Okay, now from here, from the graph, it will also tell you one thing. For any given orbit radius, there will only be one specific period of orbit. There cannot be two or more different orbit periods for the same orbital radius. What it means is something like this. If I tell you you have R1, you're supposed to have T1. If you have R2, you're supposed to have T2 only. And then if you have R3, you're only supposed to have T3. So one value of radius will give you one value of period. If you have another different value of radius, you will have another different value of period. Okay, so for one particular radius value, you're only supposed to have one particular period value. Say, for example, this one is 100 kilometer, and then the period is, say, maybe 36 hours. This one is fixed to that radius. It cannot be a case where at 100 kilometer, not only do you have 36 hours, you suddenly have maybe 48 hours, 56 hours, or maybe 12 hours for that period. No, that one doesn't work. Okay, Kepler's third law tells you that one radius will only have one particular period associated with that radius, one value only. Okay, so that one is that. Now, another thing that I should probably mention to you is how you can go and derive the equation out. Now, for the equation, t squared over r cubed equals to 4 pi squared over gm, there are two different ways to derive it. You can use either one, but the way it was derived in the first place is the same. They all come from Fg equals to Fc. So the only difference now is the Fc that you use. Either you're using mv squared over r, or either you're using mr omega squared. On the left hand side, if you use Fg equals to Fc, gmm over r squared equals to mv squared over r, what you need to do is that you want to get rid of v to get period. So v is 2 pi r over t. This one you learn from circular motion. You substitute that one in, eventually you will get t squared over r cubed equals to 4 pi squared over gm. All right. But if you use the other form of centripetal force, which is mr omega squared, you will get gmm over r squared equals to mr omega squared. You get rid of omega to give you an expression for period. So the one equation that you learned from the previous chapter was that omega is equals to 2 pi t, right? 2 pi over t. You sub in for omega, eventually you will be able to simplify to get t squared over r cubed equals to 4 pi squared over gm. All right. So these are two different ways of deriving the same equation. Generally speaking, the right one is somewhat easier to derive. It's actually the more common one. Okay, this one is the more common one. The left one is also okay, just that it's less common, all right? But I leave it to you to see which one you want. Okay, right. So the next graph, the next page shows you a graph. This one shows you the orbital period. Sorry, this one they tell you the period versus the cube versus the orbital period. And you're getting a straight line graph. Okay, this one is actually the same equation. T squared over r cubed is equals to 4 pi squared over gm. But this one, they change the axis, where this one is r cubed gm over 4 pi squared and t squared. So this one is actually this one, right? They are applying Kepler's third law for all the different planets that orbit around the sun. Okay, so from there, they produce this graph out, where they plot a graph of the orbital radius cube against your orbital period squared. Okay, now this graph, usually when you see this in your question, the thing that will ask you to do is usually to find out the gradient. You see, in your case, this one, your gradient is actually gm over 4 pi squared. You can actually find out the value of big mass M if you know the value of the gradient from the graph. Okay, that's the significance of knowing this. All right. Now, there is a particular kind of satellite that you will learn eventually, which is known as geostationary satellites. Now, what's so special about geostationary satellites is that geostationary satellites always remain above the same point on the Earth. What we mean by that is this. You see, for example, if you are standing right over here, right now, and you look up the sky, you will see, okay, this satellite over here, all right? But at the same time, you know that because you're standing on the Earth, and the Earth is rotating, with time, you will actually start to move to a different position. Say, for example, I tell you, you are currently here. This one is t equals to 0 hours. You are currently here. But when, say, maybe 3 hours has passed, you are probably going to be somewhere around here. Okay, you're probably somewhere around here already. Okay, let's just say I draw this. You're probably somewhere around here. This one is at t equals to 3 hours. Now, from that same spot, if you look back up, you will again see the satellite is at the same spot on the sky. And then after that, you say I let time run again. Maybe this time t is, say, 18 hours. You will probably be right over here right now. Okay, following the spin of the Earth about its axis. And then here, again, you look back up at the sky, you will see that the satellite is still there. It's as if the satellite is following you around. It never really changed its position above where you are. Okay, so it appears to always remain above the same point. Now, the reason why your satellite will always remain above the same point is because in the first place, your satellite is actually orbiting at the same rate as Earth spinning about its axis. What do we mean by that is that, you see, if your Earth is rotating with a certain angular speed, let's just say I give you an arbitrary value of maybe 5 radians per second. This is the spin of your Earth. This is the angular speed of your Earth spinning. Your satellite would also need to have the same angular speed, which is, in your case, maybe I just rub this one off. The angular speed of your satellite must be the same as the angular speed of your Earth, which is in turn 5 radians per second. Okay, this is what I meant by the orbit. It must be orbiting at the same rate as the Earth spinning. The angular speed ought to be the same. If they are moving with, or rather they're turning with the same speed, it will appear that the satellite is actually not moving. Okay, so apply this to the case of the Earth. We will say that a geostationary satellite has an orbital period equal to that of Earth's rotation about its own axis of 24 hours. It travels over the equator in the same direction as Earth rotation from west to east. Okay, now it's because your rotation, angular rotation, or rather angular speed is the same, you will also end up having the same period, because you can see from here, omega is 2 pi over t, right? So if omega is constant, t is also constant. Okay, you are going to have the same period. All right, so in the case of the Earth will complete its spin, will complete one spin in 24 hours. So the satellite must also complete its orbit in 24 hours. Okay, and there's one specific thing that you also need to be aware of. Geostationary satellites can only be possible if they orbit about the equator, or rather above the equator. If it is at some other angle, like say this one, or like this one, or like this one, geostationary satellite is not possible. It must orbit above the equator. In some cases, when you look at your marking scheme, rather than saying that it orbits above the equator, they sometimes word it as this: it follows an equatorial orbit. Okay, this is another way of wording the same thing. Okay, and then it must be orbiting from west to east. All right, you must follow how the Earth is spinning. Your Earth is spinning from west to east, right? Because your Earth is spinning from west to east, that is the reason why you see the sun on the east first, and then the sun setting on the right. Because your Earth is spinning from west to east, that's the reason why you see the sun rising first in the east, and then the sun setting in the west. Okay, so just something to know. Okay, these are the 3 characteristics for geostationary satellite about the Earth. Okay, you can also have geostationary satellites for different planets. Okay, but in that case, when you're talking about geostationary satellites for that planet, you just need to know that the orbital period must be the same as the spin of the planet. It must be orbiting above the equator of the planet, and its orbit must be following the direction of spin of the planet itself. Okay, so that's what geostationary satellite is.